Well, first, welcome. Thank you for showing up at the end of this week of talks. So we have an hour. There's a lot I'd like to cover, so there will probably be things I will be forced to skip. But one thing that I want to make sure you realize is all the material is online. The documentation, it's on this Read the Doc, the workshop. Everything is there, including the exercises, how to download the data you need, and also all the solutions are there too. So as I go through it, I will either be too fast or too slow. I don't know. I'm not with you in the room to feel the room and know. So I apologize in advance for whichever faux pas I make. But you will have the opportunity, and I strongly encourage you to go back to the workshop material on Read the Docs and go through it again at your own pace when you have the time. So the way the workshop is structured is I will, in the interest of time, I will define a few terms and do a few demos in the first part. And in the second part, you will have the chance to do some exercises. If you don't have Dragons working right now, don't worry. Most of the exercises is just about figuring out which command to write. So you don't even need to run it. And in fact, we won't run most of the commands we will figure out. So this workshop is not about how to reduce data, because we would need a whole day for that. It's about how to customize Dragons, how to tame your Dragons. So let's get started. And here we go. So what is Dragons? It is a pipeline, but it's not a completely hands-off pipeline. It can be automated, it can be customized, it can be run interactively, it can be scripted. It's really at the discretion of the users. But we do try to optimize all the algorithms and the default parameters such that for most of the programs, if it runs completely hands-off, it should give a pretty good result. Of course, programs are different, sky conditions are different, so that's why we also provide the ability to customize and tweak and optimize the reduction to really get the most out of your data. Currently, it is focused on Gemini data, but we do have some hooks to support other type of data. It's not super clean. I hope that one day we get to that. So yeah, we thought early on about how we could hook other data, but for now, just Gemini data. We have our hands full. We really cannot support other type of data fully. The components that we will look into today, I'm not going into the details of implementation, how they work together, but we will talk about astrodata tags and descriptors later. That's how those you can use to create your file list, and the recipe system, basically what a command reduce that we will use today. What it does, it's the infrastructure, the automation, that's what is the core. This is how it knows how to recognize the data and which recipes and primitives to use. It's through Astrodata. We have the Calibration Manager, which allows the reduce to automatically retrieve the most adequate process calibration, so you don't have to put it on the command line or in your script. And then as part of Dragons, there's a whole set of libraries of recipes and primitives for the Gemini data. Currently, the public version has support for the Gemini imagers. What it is not, and here I think it might be my most important slide of this workshop, it is not an analysis package. So if you want to measure redshift, equivalent width, do photometry, that's not it. Dragons will reduce the data up to the point where you can do these measurements, with whichever tool you prefer, but it will not offer analysis tools. It is also not a replacement for RF. RF is huge. You cannot expect us to replace that. It is, if you want to call it a replacement, it's a replacement for the Gemini RF part, which Gemini RF also is not an analysis package, it's a data reduction package. And before we go to the workshop material, And by the way, this is essentially the first two section of the workshop. A typical usage, just to get people oriented, and thank you everyone for filling in the poll. It confirmed that most of you never used dragons. So just to get you oriented, and I will do a demo of that later. A typical usage is you create your list of input data, and we have tools to make that painless. You initialize your calibration database. The database is just a small SQLite database. It takes no room. It's very simple. It's just a file. And then you reduce your calibration, make the calibration database aware of those newly reduced calibrations. And then you reduce your science. The calibrations will be picked up automatically. And the few lines, 6 lines there, well, if you had NOIRLab data, very simple program, that's pretty much all you would have to type. So it can be that simple. So with that, I will switch to my desktop. Give me a second here. Oops, not leave meeting. Whoa. Okay, share. So can somebody confirm that you're seeing DS9, the workshop material?
Yep, you're good. This is the same one.
Thank you. Thank you. Okay, so let's start defining some things. Dragons uses, and by the way, I'm sorry, I'm looking at my desktop, so I'll try to talk to you and see what I'm doing. Dragons uses a set of recipes which calls primitives. So recipes is, as you can think, it's a set of instructions that will get from raw data to your final product. The primitives are the steps in between. So if you look at the workshop material here, this is a recipe. Reduce, not very imaginative, but that's the name of that specific recipe. For those who know Python, it's essentially just a Python function. And here, prepare, add DQ, ADU to electrons, flat correct, dark correct, those are the primitives. So the primitives will affect your data, will do something to your data. And as you can see, we really try hard to name our primitives in a way that will let you know more or less what is happening. So we try to keep the scientific meaning of the step. So essentially, when you look at the recipe, you should be able to read it and have an idea of what is going on. Of course, you don't have the details of the algorithm underneath, but you have some indication, like this will dark correct, flat correct, do the sky correction, and align and stack the data. So that gives you an idea. Now, this is all good, but the first step is, how do you get to see those recipes? So what I'm going to demo now is how to inspect which recipes are available, what they look like. And then, as I mentioned, you can also customize things. Well, you will customize the inputs to the primitive. So I will show you how you can see for a given primitive which input parameters you can adjust. And we will I demo it now, but we will use those principles later in the exercises. So I'll just skip to a good demo step. So I want to know about a recipe. It's called show recipes. So it shouldn't be too hard to remember. And now one thing I always forget to do, I need to get into the right directory where my data is. So if you downloaded the data package, this is all data that you downloaded. So that's where I am. And I'll just clear this. Here we go. Okay. All right. So I want to know, I have this file, and I know that this happens to be a NOIRLab science image. And I want to know, what the recipe looks like, what's going to be run on this thing. So show recipes, name of the file. and it will show you the recipe that is the default recipe that is associated with that file, with a NOIRLab image. So the recipe tags, that's for a NOIRLab image. And this is all the primitives that will be run sequentially on it. Things that I want to point out now, and I will point them out later. Yeah, I agree, format is not spectacular, but the information that you want to be aware of is the name, the input recipe, the name of the recipe. So you know if you decide to edit the recipe, and we will do that later, that's the function you need to find. And the recipe location is another useful information. If you want to make modification to that recipe, you copy it over and then you can make modification. And again, we will do that later. So this is nice. It shows me what is the default recipe. The thing is, the recipes are grouped in recipe libraries. So the libraries, their characteristic is they will work for a certain type of data. So if I have several recipes that I want associated with NOIRLab image, NOIRLab science image, then I have a library with all those functions in there. There's always one for each recipe library. There's always one that is default. But there are others. Let's say you want to see what the others look like. Well, show recipes, the name of the file, and show me all of them. Wow, why is it taking so long? And here we go. Here are the names. It's Python syntax, but these are the recipes that are available. One thing I want to note, not because we're going to use it, but just to avoid confusion, you have two reduces. You have these things. There are actually different recipes. One is for SQ. SQ in Dragon's World is for science quality. QA is for quality assessment. So when you do show recipes -all, ignore the QA recipes. They are used internally at night to help our observers make the decision. So we do some automatic reduction at night, very crude, but just to help to figure out what the sky conditions are. So that's what those recipes are. You never want to run them. Just focus on the SQ recipe. Those are the ones you're interested in. And just a heads up, in the next release, you're going to start seeing QL recipes. Quick look for GMOS long slit. Those will be the only one available, just for quick look. Okay, so let's say I'm interested in this makeskyflat recipe. I want to see what it looks like. So again, what I will do is show recipes, name of that file, and a flag that you will see here, and you will see again with reduce, is -r for recipe. So that's the mnemonic here. I want to see the makeskyflat recipe. And I apologize, I have no idea why it's so slow. So here we go. I confirm that the recipe I'm looking at is makeskyflat. It's in the same recipe library as the other one. It's not the default one. And here's what it does. And if you're curious, and if you work in NOIRLab in the terminal bands, L, M, and M bands, you want your flat to be created from your science image when you have just 4-point sources. And you would use this specific recipe. So that's how you inspect the recipes. The next thing to inspect are the input parameters. So that's very nice. Let's say I have, let's say normalize flat. I would really like to, well, this is, yeah. I would really like to know what I can fiddle with. For some reason, normalization is not working. I want to change something. What can I change? So that is with show pars. Pars is a short version of parameters. And here in the workshop, the document, I show you what the syntax is. And I do want to talk about this a little bit. So show pars the name of the file, and the name of the primitive. Now, one common question is, well, I want to see what the input parameters for normalized flat before dark correct are. Why do I need to provide the name of a file? That is because just like for the recipes, the primitives are also associated with specific type of data. So the NOIRLab flat input parameters are likely different. Well, even if the parameters are the same, the defaults are likely different than from GMOS flat. And still the primitive will have exactly the same name. So that's why it's very important that you do add the name of the file that you're going to work on. So let's see how it works. And in fact, this one, I just want to copy paste because typing can be a bit annoying. So here, show parse, the same NOIRLab science image. I want to see what is available for dark correct. This one is a very simple one. I'll show you another one. And here we go. This one is very easy. Essentially, what you want to do is either to turn it on or off. Maybe a more interesting one will be, let's see, sky correct. This one you can really fiddle with. So it doesn't even fit on my. So reset sky, scale the sky, offset, save the sky. The operation you do to combine the sky or calculate the statistics. So you can really, depending on the data that you have, you might want to fiddle with that or experiment with these things. So with show parse, this is how you get to see what you can change. And I will show you later on the reduce command line how you can change that. And since I mentioned the reduce command line, so today I'm just working from the command line, but just know that if you're a Python coder and you like the script, everything can also be done through the API. It's completely out of scope of this workshop. So moving on. Now I will do a little demo because most of you have not used Dragons, you haven't seen it in action. This is a very, very short, much shorter version than the actual NOIRLab tutorial. So if you want to see the full reduction with a bit more bells and whistles, we have the NOIRLab tutorial that goes through those steps and a few more. So it's also on the Dragons read the doc space. So the steps, as I mentioned, you set up the calibration manager, you create your file list, then you basically start reducing. So it's really straightforward. And here I am in my reduction directory. Let me just clear it up completely, just to make sure now it's completely clean. I won't have surprises. And I'm going to reduce NOIRLab data with the calibrations from raw to the final product. And yes, it fits in just in a few minutes that I have here. We will, the first exercise is about the local calibration manager. This is the bit that actually has created some confusion. So I will try to demystify it. It's really not complicated. But maybe by doing it yourself and switching between calibration managers, it will become clear in your mind. So just so you know, it relies on a configuration file. Now, often configuration files are scary. This one is the simplest configuration file in the history of configuration files. You have calib, standalone, true. Those two lines you just leave there. You never have to change that. For those who are curious, yes, it can be false, but only at Gemini. It's an internal thing. The field that you care about is database dir. So it's just a directory on your disk. It can be anywhere on your disk. It doesn't need to be where you're reducing the data. It really can be anywhere on your disk. So that's the configuration where you want the little file to be created. And let me just go ahead and, oh, and by the way, let me just show you what my calibration file looks like, because that will give you an idea of what the exercise will be about. So this is what it looks like. Currently I'm set up just like ready for the workshop. But for each project I work on, a different tutorial or helping a user, different help desk, I create a different calibration manager. I don't know how many calibration manager I have on my disk, but they're all controlled through this database, their field. And in my file, I have a lot of them, but only one is activated. So all the other ones are commented out. Okay, so that's the key to remember. Which one you're going to use is the one that is commented out. So let's just get out of there. And right now I have nothing. I do CalDB init, and it creates this little database. And here it is. If I look into that database, CalDB list, it will say, well, I'm empty. I have nothing. I haven't started. Makes sense. If you have your configuration files set up and you have downloaded the Google Drive, the extra Google Drive files, if you do CalDB list, it should have two files, the flat and the dark. So let's start a reduction. I'm ready to go. Step one, create my list. And to create the list, it's the tool data select. At the very end, I don't know if we'll have time, but at the very end, there's a series of examples and an exercise that I think will be a take-home exercise with data select. You can really go and pick exactly the data you want to create the file list. So in this case, I want the darks with an exposure time of 20 seconds. Here I'm using tags. Here I'm using descriptors. So I want to define those two. The tags, or the astrodata tags, they're basically the nature of the file. So you will have NOIRLab flat or NOIRLab dark, GMOS image, things like that. It's really the nature of the data. Things like exposure, filter name, object, it's more like the flavor of the data. So that's what conceptually distinguishes between the tags and the descriptors. So you use the tags here, they're always in capital letters, and the descriptors in the expression. So, and the syntax is the Python syntax. So let me go ahead and quickly create the list of dark, the list of flat, the list for the standard star, and the list for my target. And it will go in the directory where I have all the data and create all the lists that I need. Okay. And here I have my list. And one thing I want to point out, let's go to, I check the flat. You could, it's Unix, so you could redirect to a file. I strongly suggest you use the -O, basically to create the output file, because it will add the criteria that you use to create that list. And I found when it's time to debug, it's somewhat useful at times to figure out how you created that list. Okay, so now I'm going to reduce the darks. Reduce, the little @ symbol is just to identify that it's a list that it needs to open. And here we go, I reduce the darks. And I don't need to specify anything else. It will open one, say, oh, this is a NOIRLab dark. Let me try to find the recipe for NOIRLab darks. Let me try to find the primitives for NOIRLab dark. Puts it all together, reduce the dark. I have my dark. It's this one here. So now I can add it to my calibration manager. And a note, just in case I forget to mention it later, it does not add the file to the calibration, to the database. It adds information about the file. So if you delete that file from here, it will still be, the information will still be in the database, but then when it reduce tries to retrieve it, we'll say, it's supposed to be there, it's gone. So when you add the information about the file, not the file itself. All right, and this, for completeness, if I do my CalDB list, here I have this file in this location. Now I'm going to reduce the flats. The flats for this type of data, it's a series of lamp on, lamp off. I send them all in, and the algorithm, the primitive, will figure out, oh, these are the lamp on, these are the lamp off, fix them the right way, and off it goes, and will give me my flat, my NIRI flat. I have my NIRI flat. For those of you who've used Gemini IRAF to do that same thing, you would have spent 2 hours already by now. So, CalDB, I add my flat. Now I'm going to reduce my standard star. And here's our first introduction to how we can customize the input parameters. So for the NIRI standard stars, the darks are not taken. So if I try to reduce the dark, it will try to, and it's in the recipe, dark correction is in the recipe, and then it will ask, well, do I have a dark? No, sorry, and it will just stop. If a calibration is missing, it will not continue. So, but this time I don't have a dark. The star is so bright, it's not going to make a difference, and besides we do the sky subtraction. So in this case, we say, well, the dark correct primitive, the do dark input parameter, set it to false, and that will stop the dark correction. It will just skip the dark correction. It will still look for it, but it just won't do it. So, okay, I'm happy, that's fine. So the standard star, and I'll show the image later actually with my next the demo. It's basically, actually, it's still right here. It looks like this, and it's a dither on target. So the usual 5-position dither, I think. I don't need to specify anything. The algorithm is smart enough to recognize that it is a dither on target. And for the first frame, it's going to use the other one to create the sky, then moves to the other one, will use the other one. As long as the time and they're shifted, it will figure out which other images it can use to create the sky frame. And here we go. I have my stack, my reduce. It's flat fielded, dark corrected, aligned stack. A sky subtracted, obviously. All right. Now I'm going to reduce my target. It looks like this. So it's an extended source. When you deal with extended source, you have to do an offset to sky. So in this list, and target that list, what I have is all my on-target observation, all my offset to sky observation all together. And again, the algorithm is smart enough, it will recognize the pattern and use only the offset to sky observation to create a sky. Now, another customization, this is a special case. My target really filled the field of view. So normally to fit the sky, the sky background with this background in your target frame. Well, this won't work very well because I have no sky in my target. It's just, it's filled with the galaxy signals. So I want to turn off the scaling. The sky were observed soon enough, it should be a good representation. So in this case, again, the primitive sky correct, scale the sky, not turn it off. False. And here we go. Now I want to point out that it will be dark corrected and flat field corrected. I did not have to say what to use. The calibration association is being done automatically. So the system goes, okay, I'm supposed to have a flat here. Calibration Manager, do you have a flat for this data? And it will do the association. The association rules are the same as the one used in the archive, literally the same code. And it will look at, yeah, I have this one. Here you go. And it does it. Now, it is possible to override this. And there's a section we're going to skip, but the information is there in the workshop material, how you can override the calibration selection. So here it is looking at the sources, trying to figure out the solution to align my frames, and I have my stack. And we have gone from raw to reduce in a few minutes. And this is, if you're curious, this is what it looks like in here. And if you zoom in, the alignment, the automatic alignment is actually really, really good on this one. So that's what Dragon is. Now you produce stuff you might want. I said it's not an analysis package, but we do provide a tool to actually display the image, because otherwise it would be a bit annoying. So we use reduce, and there's a primitive called display that we can call that will display to the S9. For something like NIRI, it's just one image, so it's fairly straightforward. But for GMOS raw data, when you have various amps and different extension, and not necessarily in the right order, display knows how to piece them up together and display a nice image that we can inspect. So especially for GMOS, this is particularly useful. So let's just do reduce -R and display, and it will display the stack. And here, one thing that it does is it will label saturated pixels. So sometimes that could be useful. And the other one that I want to introduce you is inspect, which also display the data, but it will display, for example, a list. So one thing that I recommend, I always do myself, and I recommend that you do, is before you start your reduction, you create your list of raw data and you inspect them all. Now, typing reduce R display for each one of them would be quite painful. So there's inspect instead, which will loop through the data in your list with a pause of, the default is 2 seconds. You can adjust it to whatever you want. And let's do this. Let's see it in action. And here you don't want to do the necessary measurements, but I really like to look at my data to catch anything that might be a bit odd. It's rare that it happens, but it does happen. So, and I'm a bit paranoid, so I always inspect my my raw data. Okay. Now get ready. It's your turn. Before we get too tired, we're going to look at the local calibration manager. Essentially that's the only topic where if you want to fully participate, you need to have a working Dragons environment. But the other ones, it's not necessary. You'll be able to follow even if you don't have a working Dragons environment. So if you have installed Dragons and you're set up correctly, you should already have a file in .gemini.dr, the file rsysconfig, that looks something like this. And if you want to check that it's configured properly, caldb config will tell you how it is being configured right now. So that's the file it's using. This is the directory that is specified. And this is basically the file with the directory that is going to be used. So if you've downloaded the Google Drive data, your playground directory should look like this. There's a calibration, cal manager, sorry, PB, and that's the one I just created in my case. And if I do the caldb list, there are two files, the flat that I just created and the dark that I just created. So assuming that you have this set up, and remembering what I introduced earlier that I will remind you about, is if you want to switch to another calibration database, all you have to do is go to the configuration file and create a new database dir field and uncomment it, comment the other one. So that's how you switch. Just activate the one you want to use. And to create one, when it's not being created, you do caldb init. Caldb init, you do that just once. Just I realized as I was preparing this that it should really be called CalDB Create, because that's just what it does. To activate it, it's really just a configuration file. So if you want to activate it, configuration file. If you want to create it, CalDB in it. So your first exercise is, so I have a CalDB, a Calibration Manager in this playground directory. I want you to create one in another directory. Let's just say just above that, just the directory above that. It really doesn't matter where you decide to create it. So I want you to go to the calibration, to the configuration file, create a new database there, activate it, CalDB in it, and then do a CalDB list to show that it's completely empty. So I'm going to give you a minute to try it. I'm not going to actually time a minute, and don't worry, give it a shot. I'll start. I'll show you exactly how to do it. So, your turn. I can tell you, as a presenter, it's very odd waiting for people to do something when the people are not present. If you want to follow along with Calibration Manager, the configuration file, I comment out the one that was activated. I activate the new one. One thing that I recommend you, well, I do all the time, I recommend you play with it as well, is CalDB config. If you have, if you go from project to project, make sure with CalDB config that you're pointing to the right calibration manager. You might get some surprises if you start using the wrong calibration manager. And here it confirms that now I'm using this calibration manager, and it also tells me, wow, it doesn't exist though. So do initialize it. So if I just go, it's not there. Oops. Now it is there. And I can confirm that it is completely empty. Right. Easy peasy. Now just an overview of the usage. There's another exercise. The usage, I've introduced CalDB config. Just use it a lot just to make sure you're looking at the right database. CalDB list, it's also useful. We've used CalDB add. And again, reiterate, it doesn't add the file, it adds information about the file. And CalDB remove, if you want to remove knowledge of that file from the database. And again, it will not affect the file on this. The file on this will stay there. It's just going to be removed from the database. So the other exercise is we have a new calibration database. I want you in the playground, you have a flat here and a dark. Just add the flat to this new calibration database and confirm that it is there with the CalDB list. And then go back to the configuration file and reactivate the one in playground and check that now you see two files in that database. So once you've experienced how to switch the calibration database like that, hopefully you'll feel more comfortable working with them. So I'll give you a few seconds to play with that. So to add the flat is CalDB add. And I confirm with CalDB list that now I do have one entry for my flat. Now I'm going to switch back to Playground by editing my configuration file. Activate Playground, deactivate array imaging tutorial. I don't need to do an init now because it already exists. I can just do a CalDB list. And indeed, I'm back in my original calibration database with the flat in the dark. So yeah, before we leave the topic of the calibration database, it could work if you decided to have just one gigantic database. Could work. I don't think it would be a performance issue. I think scientifically it might be safer to have different calibration database for each project you work on. That is certainly my preference. All right, let's talk about reduce. If you want to see all the flags that reduce can accept, just do the standard -h or --help, and you will see the long list of things. We're just going to cover a few of them. The first one I want to talk about, it seems trivial to talk about it, but it's linked to a question that we get from time to time. When you run reduce, you cannot set the name of the output file. And the reason is because you don't really know how many files you're going to have. It really depends on the recipe that gets selected. It might produce 50 files or it might produce one file. And when it comes to the implementation, it's a bit difficult to figure out a solid way, robust way to deal with that. So for the time being, what you can change is the suffix of the output, because you said that suffix, whether there's one file or 50, it will apply without name collision. So that's why only suffix is, changing the suffix is allowed. And it's very simple, -- suffix equal the suffix you want to use. By the way, the equal is optional, so you might see me use it or not. So now, more interestingly, and we've seen examples of that, is how to customize the primitives, the inputs to the primitive. As a reminder, if you want to see what you can change, you can do a show parse. And here, let's show parse the normalized flat. And here because remember, you need to provide a file name. Well, normalized flat, usually I'm using a flat for that. So that file happens to be a flat. How did I know it was a flat? Well, I can check my flat list and I can pick any one of them in my show parse. I just happen to pick the first one. So this going back to the show parse output. So for normalized flat, I have the name of the parameters that can be changed. In this case, well, you have the default value. In this case, this one accepts a set of different values. So that's a key. So sometimes it's a range. It will tell you what it accepts. And finally, as a reminder, it's reduce, name of a file or a list of file, -p, p for parameters, the name of the primitive, column, the name of the parameter, and equals the value, the new value that you want to use. So an exercise for you. I've already showed you how to do, well, it's like right up here, how to see the set of parameters that you can change. Now I want you to come up with the reduce command that will change the scaling to use mean instead of median. So just since you didn't run the demo, just a reminder, when we reduced the flats, it was, oh, is that 15 minutes, Jamaica?
Yes, it is.
It is? Okay, okay. So reduce flat, that's what we use. What do we need to add here in order to change the scaling on the normalized flat primitive to mean? Give you a few seconds. Think about it. All right. Dash P parameter. I'm working on normalized flat column. And if I look here, statistics for scaling, parameter is named scale. So scale equals, and to do the mean, it appears it's just mean. And then I would hit enter and run it. So that's how I would customize it. If you have several customizations like that to do, you just keep adding strings like that for each one of the primitives and parameters you want to change. You don't need to repeat the dash P. As long as they're all after the dash P, it's good. Okay, running a non-default recipe. So let's go here. Well, as I mentioned, to see what non-default recipes are, you do the --all and show recipes. So let's say I want to run the makeskyflat recipe. Well, we've already seen how it works, except we used it on the primitive. And it's basically reduce my list of files, -r, R is for recipe, although it works on primitives as well. So, but think recipe. And the name of the recipe. So now what I want you to do, we want to run makeskyflat here. Actually, I think that's, yeah, makeskyflat using the target image. So in the demo, we use reduce target.list. What do we need to add to run the makeskyflat recipe instead of the default recipe? A few seconds here. Right? /r makeskyflat. And if you're experimenting, I introduced a suffix ahead before. You like suffix test sky flat, or this is my sky flat instead. So it's the suffix can be useful when you start experimenting. For example, you just add it to the call. I mentioned earlier that you can override the calibration association. This is how you do it in section 7.4. It explains how you do it. We do not have time to go through that. And it's actually fairly rare that you have to do it, but we've had a few cases when it was required. Just know that it is possible. You can do it. Now, I do want to take some time to show you how to modify a recipe. And the most common case that I've seen so far was related to people who wanted to see the intermediate output. Because as you've seen, when I reduce the data, I start from raw and I end up with the final product, which is great when everything works fantastic. But there's some cases where you might want to see, okay, but what does it look like after the flat correction? What does it look like after the sky correction? So in that case, that's a classic case of you wanting to modify the recipe, and that's entirely possible. So first thing you need to know is, where is that recipe? What is the recipe and where's that recipe? And that goes back to what I showed you earlier. The show recipe name of the file. You will have the name of the recipe. That's the function def reduce name of the recipe, and the recipe location. You might, just a note, you might see that some cases, I cannot really reproduce it all the time. Sometimes you get the .pyc. Well, just copy the file is the .py without the C. So I kept it in there because I think it happens sometimes, and it's information that might trip some people who are not familiar with Python. So I'm gonna do, because I think I'm in slightly different environments, I'm gonna show the recipe. That's how you would get the file, the recipe library. So recipe, you have information, this is where it is, that's the file. So I'm just going to copy this in my current directory. I always like to rename the file. It's work. I don't think it's necessary, but I just always rename it. So I know this is the one I'm missing. And now it's right here in my directory. And I think you should have it if you downloaded the Google file. And if I just go to it, then I have, it's just a text file, normal Python script. Reduce is the one here that I can edit. If I wanted to make changes to makeskyflat, I would go to the next one. This is a recipe library. There are more than one recipes. And if I wanted to add see the intermediate output after the flat correct, what I do is write outputs. That's the name of the primitive. It write outputs. Convenient name. Let's say after the strike correction, write outputs, and they will be given the suffix associated with the primitives just before them. So I think after this one, it's either memory underscore sky corrected or underscore sky subtracted, so something like that. So it should give you, and the top one would be underscore flat corrected. So it gives you an idea of which one is which. So that's how I would do it. Now, I'd like you to do a little exercise, edit a recipe. This time we're gonna edit the flat recipe. Let's say I want to see the output just before the normalization. The output of, I'm reducing flats. And for some reason, I want to see the output just before the normalization. So how would you do that? So maybe in the interest of time, I'll go, I'll just demo it to you. So I would do, first, I need a flat. So let's find myself some flat. This one is a flat. Show recipes. This one. That's the location. That's the name of the recipe library. I'm going to copy it over. My nearly flat recipes. And then I go very flat recipes, make process flat, and the same deal. Just go, whoops. Oh. Write outputs. And then I'd be able to run that. Now, how do you run this? Here you have the syntax. It's basically -r again, -r is your friend. Now you need to provide the name of the file that you've just edited. And then it's the name of the recipe that you want to run. So in my make process flat recipe, I would do reduce flats. Yes, I'm gonna move on. -r my nearly flat dot make process flat. And that's how it will know to not go try to find a recipe. It will just use the one that you've specified here. And I'm completely run out of time. Have a look at the final one. This is the really fun one. But it's not very complicated, but it's something you can have fun with. It introduced 3 tools, type walk. We use the tags. Well, you need to know which tags are available. Well, type walk will basically go through all your files and list all the tags for each one of your files. So that is useful when you want to try to figure out which one's which and which one you can use. Show D is for descriptors, and you will see that the descriptors, the names are very descriptive. If you go, you have links in there that will lead you to the list of the of descriptors. And let's say I want the exposure time. Well, go through the list, and it's exposure underscore time, filter name, filter underscore name, UT date, UT underscore date. So you shouldn't have too much problem figuring out what you want to, the name of what you want to look at. And then with that, you can just basically show -d, the name of descriptors, and it will just list a nice table. Let me just, here's an example. If I want to see the exposure time, filter name, UT date for all the files, it will list me a nice table with all the information. So that's useful again when you use the data select next. And here I have several examples for the data select that will use the tags, the expressions, and it is possible in the expressions, it's possible to use the and or, it's all Python syntax. And that's your take-home exercise, this one. It's not super realistic, but it will really exercise the data select features. And I'll stop here. Sorry, it was a bit rushed, but I hope that you have the chance to go back and do it at your own pace. You have everything you need, including all the solutions. So I have, we have like technically 3 minutes to answer questions. But frankly, I do have some extra time, maybe another 10 minutes afterwards. I do have another commitment, but personally, I have some extra time to answer questions. And any questions that you put in the Whova app, don't despair, I will go and answer them all.
Okay, Kathleen, so can you see the questions in the Whova Q&A for you, or would you like me to read them?
Yes, no, I see them. Would be tough for you to read the second one, the essay warning.
That's why I was checking.
This one, the essay warning relationship, this file, I have no idea what this is. And maybe I'll get in touch. Yeah, I've never ever seen something like that. I think there's something really wrong with your installation of the Dragons environment. I think it's related to, I'm not sure, I'm really not sure, but I think it's related to some SQL package or some database. There's something odd going on here. CalDB init database is not configured as standalone. That's probably because your standalone was set to false. Usually that's the problem. Another problem that I've seen with the init or in the Cal database is if the directory that you specify, it must exist. If it doesn't exist, I think in the public version, it just will keep continuing very happily, but will be really, really messed up. We've faced that one like less than a month ago, so we went on and fixed things a bit to make it a bit clearer. But that's something that we saw. So standalone. Is it Caleb? So yeah, that's, so those are debugging questions, and I will go back and try to figure out and help you out with these things. Any other questions? So I see that there were a few votes. So that the CalDB won. If you vote, that means that a few of you did get this problem. So keep an eye on it, and I will, if not before my other engagement, later on tonight or tomorrow, I'll answer the technical questions that you have there. We'll try to figure it out. Anything else? And by the way, I would really like to get your feedback on this. This is a brand new workshop. Very first time I gave it. Nobody else got that one before. So you were my test participants. Thank you very much. And if you can share your feedback, it will be very useful for the next group I present to. Oh,
I'll just come on and say thank you, Kathleen. And thanks everybody for coming. And it's been a great workshop, and it's been a great meeting for those of you who are still here. and have a good day, afternoon, evening, wherever you are.
And have fun with dragons and keep an eye out for the next release. The GMOS spectroscopy stuff is really cool.
Awesome.
Thank you, everyone. Bye-bye.
Bye.